questions, confusions, doubts regarding the assignment? Most of them popped up in the last 24 hours, which is not a good thing. I know, I've been there. I understand how it works, but it's not a good thing. I cannot help you as much if you start looking at it and realize you have a problem the night before. If I go to sleep, I go to sleep. So try to do it before, so you have time, so you don't have to waste your bank of unexcused absences on. But let me try to address, I mean, I know you had to submit it. Maybe some of you have asked for an extension. Let me try to clarify it.
You didn't want our sample.
I don't remember. If I asked for it?
No, you did not ask.
If I didn't ask for it, then no. Okay. I gave you guys a unigram distribution that I asked you to consider as the ground truth, as if that's the true distribution. So I put you in a situation where you're God, when you know the truth about the world. And I ask you to generate a sample from it. And the sample is called sample 1 or S1. And then I ask you to define words, or the vocabulary is defined because you're given the unigram distribution. So that implicitly defined the vocabulary. And now you can categorize each word as having occurred 0 times, 1 time, 2 times, 3 times, any number of times. And now I ask you to define a set of words that happen to occur exactly once in that sample. We call that the singleton set of S1. So the singleton set of S1 is one specific set of words. True, for different people it will be a different set because you generated different samples. But for you individually, it's one fixed set. It's not an abstract, generalized concept. It's one very particular set that you can look at, hold in your hand. And that set defines the event. E2, I think, was the event that consisted of, the event is, in the nature of events, they are binary. Either they occur or they don't occur. So the event E2 occurs if any of the words in the singleton set of S1 occurs next. So, for example, if you have a word frequency list, and it starts with large numbers and goes down to small numbers, 5, 5, 5, and then goes down to 1, 1, 1, 1, and then 0, 0, 0, 0. You take these words, however many they happen to be here in your particular set, and that defines the union of that set is E2. And now I ask you, what is the true probability of E2? And that's basically the sum of the true probabilities of these individual words. And the same for E3, which I think was these words. I deliberately put you in a situation where you know the true answers, which is a situation we're almost never in, just as a way of helping you see the accuracy of the different ways of estimating it. Okay? And the other thing to remember, and that may have been a confusion, is that I was asking you to estimate the probability of E2 as a whole, not of a particular word inside E2. Okay? That may be completely clear to most people, but there were enough people that it wasn't clear to, so I thought I should mention. Okay, we are well into the course and we're ready to tackle sentences. It's amazing how much complexity you can find in something as simple as words, but let's now look at sentences. So we want to estimate the probability of a whole sentence, which we can write as a sequence of words. Word 1, word n, followed by a end of sentence symbol. The reason I put the end of sentence symbol here is because I want to estimate the probability that as I go along generating one word at a time, I will end up generating this as a complete sentence, not just as the initial part of some longer sentence. So the event is defined as, I've generated these words, W1 to Wn, and that's where the sentence ended. So this symbol says that's where the sentence ends. I want to estimate this. Estimate this from a corpus. So the most straightforward way to estimate from a corpus is maximum likelihood estimation. Right? So P maximum likelihood of a particular sentence, which I'll just call S, is the number of times this sentence was seen in the corpus divided by the number of sentences in that corpus. I use n sub s because I've already used big N by itself as the count of the number of words. So n sub s is the count of the number of sentences. Is this a biased estimator? Yes? No?
Yeah.
Yeah? Okay.
Many sentences that didn't occur that don't have probability 0, we estimated it.
Okay, but that doesn't make the estimator biased.
Sorry.
So I know where you guys are coming from. I think you're all right, but you all mean different things. So as an estimator, if that's all, I'm not given any data. I'm just saying, what is this? If this is my rule of estimation, it is unbiased. Relative frequency estimators are, for the most part, unbiased. It is true that if I use it to estimate sentence that occurred 0 times, it is going to give me a biased low estimate. And if it's used 1 or more times, it's biased high estimate, just like with the case of words. But as an estimator, before I condition it on the data, it is not biased. However, it has a huge variance, much larger even than the variance of applying it to individual words. Right? Because most sentences in the world, including sentences that are reasonably grammatical and likely to occur, most sentences in the world that are of significant length have never occurred in your corpus. Right? It's an extremely sparse, unbiased, but huge variance because extremely sparse. So we're going to live in the world of extreme sparsity. Even the world of individual words is already very, very sparse. Sentences are exponentially more sparse than words. Comment?
I think it's not that the variance is large. The coefficient of variance is large. So
The what? The coefficient?
So the probability is small. So the variance is, I think, p times q. So it is small, absolutely. But
I see. Well, that's a good point. The point is that all these probabilities are going to be very small. They're going to be either 0 or 1 over n sub s or 2 over n sub s. Very few sentences occur, 10 times n sub s. All these numbers are extremely small. Even for the most common sentence in the world, this number is extremely small. Therefore, the absolute measure of what the variance is, if you think of variance as a quantitative measure, it's going to be a very small number. But the variance, the relative variance, is going to be very large. So if you think of the variance or the standard deviation divided by the mean, that's going to be very large. Okay. That's what we mean when we say huge variance, huge relative variance. Okay, that's going to be the case almost always. So the standard way of dealing with sparse estimation is to make assumptions and to introduce some kind of a structure that if we believe there's nothing about sentences, they're all different from one another and they're like stars in the universe. Well, even stars in the universe come in hierarchies, but if they are just a huge collection of different categories and they mean nothing relative to each other, then we're stuck. There's really not much we can do. But if we think there is some underlying structure, there is some hierarchy, we can take advantage of it. And one way to start trying to take advantage of it is to break down the probability into a sequence of probabilities using the chain rule. The chain rule does not need any assumptions, does not assume anything. It's always true, and you can use it in many ways. So for example, we can write P of W1 through Wn, end of sentence, can be written as P of word 1 times P of word 2 given word 1 times P of word 3 given word 1 and word 2, all the way through P of the end of sentence symbol given word 1 through word n. This is completely legitimate and mathematically correct, no matter what the probability distribution is, right? This is just a chain rule. In fact, this is not the only way to use the chain rule. I can use it in any way I want. I can say this is also equal to P of word 7 times P of word 3 given word 7 times P of word 1 given word 3 and word 7, all the way to P of word 5. Did I ever use 5? No, I didn't use 5 anymore yet. Word 5 given word 1 through word 4, word 6 through end of sentence symbol. In other words, I can choose different components of the solution in any order I want. Okay? I can also write it as P of word 4, word 6 together times P of word 3, word 1, word 2 given word 4, word 6. In other words, I can predict them in chunks. I don't have to do one at a time. So I can do anything I want in this stage, and it'll be mathematically correct. The question is, will it be useful down the line? That's a different question. But the chain rule itself does not need justification. A bit of what I mean by this notation. When I write something like W2, I mean that the random variable W2, namely the thing that takes on the value of the word in the second position, is some particular value W. When I write W2, when I write something in the conditioning, I mean the same thing, that the random variable in position 1 takes on a particular word type, word 1. So this is the word type. This is actually an index of word token. This is a little sloppy notation. So this is why I wasn't worried about moving the end of sentence symbol to somewhere in the middle. Basically what this is Wn minus 1, n plus 1, sorry. Wn plus 1 is end of sentence. W6 is this particular word, and so forth. All right, I'm going to stick with this one, with the chain rule applied from left to right. So let me erase the others. And let me write this one as a product of P of Wi given W1 through Wi minus 1. And I goes from 1 to n plus 1. Right, because we said that Wn plus 1 must be the end of sentence symbol. So now I converted my problem from one of estimating the probability of a whole sentence to a uniform looking problem of estimating the probability of a particular word in the context of a string of other words starting at the beginning of a sentence. If I start at the beginning of a sentence and I go up to one word before this, I call this the history. This is history I, which means it's the history, it's everything that happened up to but not including position I. And I'll also call it HI. So now I'm down to estimating quantities of this type. P of some word I, namely what is the probability the particular word will occur in position I given all the words that occurred just before it. And then I will multiply them. So this is what I'm after. So far, I did not make any assumptions. This is exactly identical to this. Not to the maximum likelihood, to this, which is the probability of the entire sentence. No assumptions were made here, no approximations. Now, how would I estimate something like this? The maximum likelihood estimate of it I will write it without the I because it applies at every I. What is the maximum likelihood estimate? It's the number of times this history occurred followed by that word divided by the number of times that history occurred in the corpus. So find out how many times that history occurred in the corpus, and then find out among those how many were followed by that particular word, right? Again, to make sure that we understand what this shorthand means, it means the number of times the random variable, call it h, takes on the value small h, and the random variable w takes on the value w, divided by the number of times the randomness value h takes on small h. This is the random value that takes on the particular value of the history. For example, if our corpus consisted of, there was a little girl, oops, this is our corpus. We will view the corpus as using a moving window of history and word pairs. So the first history 1 and word 1 is the null set or the null list. I'll write it as null list. And the word, so, okay, the null list would be here, and the word will be the. There, thank you. And then the next pair would be H2, W2. It will be, the history will consist of just there. And the word will be was. All the way through H1, 2, 3, 4, 5, 6, H6, W6 will be, the history would be there was a little girl, and the word would be end of sentence. So my training data will consist of these 6 pairs, ordered pairs, and the count of each one of these will be 1, and the count of any other possible pair would be 0. Of course, in a very large corpus, many short histories will be repeated many times. Specifically, if the history is the null history, it would repeat it as many times as there are sentences in the corpus. And if the history is just one word, let's say the word there, every sentence that started with there would be, it would repeat, but not all of them would be followed by was. So you take your corpus and you pass this window at sentence boundaries, and you turn your corpus into a set of pairs, H and W. And then you can use these pairs, here are the counts, you can use them to derive a maximum likelihood or relative frequency estimate. What can you say about this estimate? This one. Is it biased? It is not biased. It's a relative frequency estimate. It's not biased. but it's very sparse because the space of possible history words is very, very large, and any reasonable size corpus will not be enough to see most things multiple times. In fact, most history word pairs will be seen 0 times. The vast majority of them will never be seen. And of those that are seen, the vast majority will be seen once. And of those that are seen more than once, the vast majority will be seen twice, and so forth. Still sparse. Very sparse. And therefore, the maximum likelihood estimator is not good. Please?
So the original estimate would estimate 0 probabilities for things that weren't seen, whereas this one, if the history hasn't been seen before, that's undefined. So the whole other
True.
things are undefined too.
True. Thank you. Thank you for pointing it out. Not only does this has a problem of sparsity, but it also has a problem that many times it's not defined because the denominator is 0. Thank you. So now I need to start making simplifying assumptions. What are reasonable simplifying assumptions to make for the general case of probability of some word I being conditioned word 1 through word I minus 1? This is the thing I'm trying to estimate. What is a reasonable assumption to make to simplify and make the estimation more feasible? Okay, so the assumption we're going to make is that the way word in position I depends on the history is mostly through its dependence on the last few words of the history. Is this a reasonable assumption? Yeah. Is this a statement about statistics or about linguistics? Linguistics. It's a linguistic assumption. It comes from what we know about language. It doesn't have to be true in other areas. Throughout what we're going to do the rest of the course, I'd like you to keep in mind, are we doing statistics or are we doing linguistics? Now we're going to, it's the first time, well, I don't know if it's the only time, but the first time today that we're doing linguistics. Everything I've done so far is just chain rule. It applies to anything in the world. It's the first time I'm justifying it by the fact that we're dealing with language. Yes, we all believe, from our intuition, that the identity of the next word depends much more on the last few words than on what happened before it. Not completely, but it's a reasonable approximation. How many words back should we look? The last word? The last 2 words? The last 3 words? I don't know. Well, let's consider these 3 possibilities. I guess there's a 4th possibility, not looking at all. So let's start by looking at the following approximations. I could approximate it with the probability of word I given the last 3 words. So it's wi minus 3, wi minus 2, wi minus 1. Or I can look at it as being approximated by the last 2 words, wi minus 2, wi minus 1. Or I can look at it as being approximated by the last word. Or I can even estimate it conditioned on nothing. Now, I didn't put heads here. This is the true target, true goal. Or just the goal. Our goal is to learn this. And we're going to approximate it by any one of these. Which of these 4 do you think is a better approximation than, which of these are better of these 4? Which is the best approximation among these? The top one.
It depends still. I mean, if you still run into huge problems of sparsity, then maybe taking a shorter history may be better.
There's no sparsity discussion yet because I'm talking now about true probabilities. Suppose you could ask the oracle to give you one of these 4 and to use it. Which one do you expect to be closest to this one? The answer is this one. Why? Because it takes into account more of the context. So it's the true, we're not talking about true distributions, not about estimates. This is the closest. This is less close, this is less close, this is less close. Right? But now, we don't have an oracle. We have to estimate them. How are we going to estimate them? We're going to use relative frequency to estimate them. So this one will be estimated by the count of, well, this one we know already. It's this one. It's this estimate. This one is going to be estimated by count of Wi minus 3, Wi minus 2, Wi minus 1, Wi, divide by the count, I'll write it like this so it matches, count Wi minus 3, Wi minus 2, Wi minus 1. This one is going to be estimated by the count of Wi minus 2, Wi minus 1, Wi, divide by the count of Wi minus 2, Wi minus 1. This is going to be estimated by count of Wi minus 1, Wi, divide by count of Wi. And this one is going to be, thank you. And this one is estimated by count of Wi divided by n, number of words. So this is just a standard relative frequency estimates, which are the associated maximum likelihood estimates of these distributions. Now my question to you is, we can call this the P maximum likelihood of, so let's give them the names. This is a 4-gram, right? 4-gram. This is called a trigram. This is a bigram. This is a unigram. And this is the 4-gram maximum likelihood. And this is the trigram maximum likelihood. And the bigram maximum likelihood. And the unigram maximum likelihood. So it's important to keep in mind the difference between the true distributions and some particular estimate of those true distributions. This is the maximum likelihood estimate, and there may be other estimates of these distributions. These are true distributions, which in turn are approximations of the one we're after. Now my question about these estimates is, which one do you think is a better estimate of its associated true distribution? They're all maximum likelihood estimators. Therefore, they're all unbiased. Unbiased as estimators of this function, right? This is an unbiased estimator of this true function. This is an unbiased estimator of this true function. This is an unbiased estimator of this true function, etc. But they all have variance. Which one has the greatest variance? Sorry? Can't hear you. The bottom has the highest variance. Why? Which counts are likely to be bigger? The counts of individual words or the counts of a 4-gram? Individual words are likely to be bigger numbers. So the numbers involved here are likely to be bigger than the numbers involved here. As a result, the variance will be smaller. So there is less variance here. Variance goes in this direction. Variance grows like this. Or more variance. It's the direction of more variance. Or in this direction, there's less variance. We can actually go to the extreme. What's a 0-gram? A 0-gram is just 1 over v. It's a uniform distribution. Doesn't use the data at all. It's maximum likelihood estimator is just 1 over V. It's itself. It is unbiased and has 0 variance. So the zerogram has 0 variance. It's just a constant uniform. The unigram has some variance as an estimator of its target unigram.
Zerogram you said is unbiased?
Zerogram is unbiased as an estimator of the zerogram distribution. So when I ask about bias, I'm talking about this as an estimator of this, or this as an estimator of that. Okay? These are the true n-gram distributions. These are their estimates, particular estimates, and this one has the most variance for estimating this. Now if I have to choose, obviously I don't have these. This only the Oracle has. I do have these. I have access to this. And I have to choose among them. I prefer to have less variance, right? But I'm not interested in estimating these. I'm interested in estimating this original distribution here. We said that from this distribution to here is a smaller distance than from here to here, right? In fact, what is the bias of this distribution of the P 4-gram maximum likelihood relative to P of word given history, relative to our goal? Well, remember that the bias is the expected value of this minus the true distribution, right? Definition of bias is expected value of the estimator minus the true value of the estimator. Remember that? The expected value of this is exactly this, because it's an unbiased estimator of the 4-gram. And therefore, the bias of this as a function of our goal, bias of this when it estimates our true goal, is the distance between these two. So I introduced a little subtle concept here. I talked about a bias of an estimator relative to whatever it's trying to estimate. Until now, it was pretty obvious that we're always trying to estimate the same thing. But now I'm thinking about this estimator, how well it estimates this versus how well it estimates this. And the answer is, when it estimates this, it's unbiased, because its expected value is exactly this. But when it estimates this, it is biased. And the bias is the distance between these two. So this is the distance, some measure of distance between distributions, between the true distribution, I'll call it, or the goal distribution, P goal, minus the true 4-gram. Notice I did not put a hat here. I reversed the order here, but I did not put a hat. Here there's no hat. Here there's a hat. Right? Because the expected value of the 4-gram maximum likelihood is the 4-gram. Right? I hope I didn't confuse you too much. Let me try to rewrite it in a more organized way. There is a goal, P goal. It is P of word given the full history. There is a particular n-gram estimator, call it, let's say, trigram. I'm sorry, particular trigram true function, which is P of word I given word I minus 2, word I minus 1, word, good enough. This is a true function, true fixed function. It is pretty close to this one. There's a distance between them. There's some distance, which I will write as distance from P goal to P3G. Then there is an estimator, specifically the maximum likelihood estimator, has a hat. The expected value of this estimator, because it is a maximum likelihood estimator of the trigram, is the trigram, right? Because it is a maximum likelihood, it is unbiased as an estimator of how it was derived. So its bias is 0. But the expected value of this estimator, trigram maximum likelihood, minus our goal distribution, I can just plug this in there. So it's the distance between the goal and this, which is this. This is the bias of the trigram maximum likelihood estimator when it estimates what we really care about. And since you agreed with me that this is closer to the goal than this, and this is closer to the goal than this, and this is closer to the goal than that, the distance here keeps growing. And therefore, the bias of these estimators grows this way. This is more bias, and this is more variance. So the variance grows as you increase the order of the n-gram. The bias grows as you decrease the order of the n-gram. So this is the choice of which order n-gram to use is a classic case of bias-variance trade-off. I hope I didn't make it more confusing than it has to be. But this is an important point, so make sure you mull over it and you get it. Of course, it's important not just for language and not just for n-grams. In general, when you have a hierarchy of models, one more detailed than the other, the more detailed model tends to have less bias, but more variance. The more detailed model has more variance because it needs to estimate more parameters, and it would be based on less data per parameter, and therefore it'll have a higher variance. Why does it have a lower bias? Because the space of functions expressed by the more detailed model is larger than the space of function expressed by the smaller, lower order model, and therefore it is closer. The closest approximation, if you have this is a zerogram, it's a single point. This is the unigram, the space of all unigram distributions. This is the bigram, the space of all bigram distributions, which includes the unigram distributions, and so forth. This is the trigrams, and here is the true goal. If I'm going to estimate this using trigrams, I can choose a function here that is pretty close. And as long as I have enough data, I will zoom in on exactly this point. I'll be closest. If I restrict myself to unigrams, the best I can do is come to here. On the other hand, since I have a finite amount of data, I'm not going to stick to this point. There's variance. So there's going to be a big cloud whose center is here. It's going to be a big cloud, whereas the zerogram has a point cloud. It doesn't really have a cloud. It's a single point. And the unigram has a much smaller cloud. It's the same idea that we saw in shrinkage last time. You can choose between estimators that come from that are randomly selected for you from one of the clouds or the other clouds, right? Would you rather choose a cloud that is closer to your goal, whose center is closer to your goal, but the cloud is wide and therefore who knows what you're going to get? Or would you rather choose a cloud that is centered further away from your goal, but is more condensed and therefore you're going to get something here? Well, the answer depends on how much it's going to cost you to be wrong, and depending on your loss function, how wrong you're going to be and how much it's going to cost you. If your measure of goodness or your optimality criteria is mean squared error, then you should look at squared bias plus variance. If your optimality criterion is different, you should look at something else. But this is your trade-off. That makes sense. Okay, so the different order n-grams give you a choice of trade-offs, of different bias variance trade-off points. And of course, I've put some of you to sleep. I apologize. I don't know why. Wake up. No, nobody was really sleeping, but they were. I could tell in your eyes. What can you do other than choose among them? You can get more data. You can always get more data, and you should. But what can you do other than get more data? Yeah. Combine them. What do we call it when we combine estimators of different bias variance trade-off? Interpolated. And the new word we learned last time? Shrinkage. You can shrink them together. Interpolation is a fine choice of word too. So we're going to interpolate them. Let's try this. Shrink them together. So we're going to estimate, we're going to have a new estimator, which I will call it the linear interpolation estimator, of the word given the history. By combining together, I will call these models P0, P1, P2, P3, standing for the 0-gram, unigram, bigram, and trigram. J goes from 0 to 3, Pj. These are estimators. Each one is built as a maximum likelihood estimator of its respective target function. And this is Pj. And in general, Pj is also a function of a word given history, except we understand that P of 2 only looks at one word in the last word in history. Of P sub 3 only looks at the last two words in history, and so forth. So we can still write it as a function of the entire history, but we understand that it only looks at the small part of it. And linear interpolation means that we combine them using some lambda j's, where the lambda j's are between 0 and 1, and they sum to 1, from 0 to 3. Yes.
What's the subscript on the P hat there? Li?
Li, linear interpolation. You can call it anything else too. And we know from Stein's paradox that since we're combining three or more components, we're combining 4 here, the result is likely to be at least theoretically better than any one of the components, in some sense of better. In practice, actually, it's going to be a lot better for our purposes. So we would like to do that. We can think about it as a way of trading off bias against variance. Another way to think about it is that many of these estimators have zeros. And if your goal is mean squared error, you don't care so much if you have zeros. But if your goal is likelihood, you don't want to have zeros at all. And combining them will get rid of the zeros. Which component will make sure you never have zeros? P sub 0. Remember, P sub 0 is the uniform distribution 1 over V. P sub 1 is the unigram distribution. It's just count of the word over n, and so forth. And now the question remains how to choose the lambdas. I'll call the lambdas, lambda bar is the vector of lambdas, of weights. So we have a corpus. We trained our 4 models on it using simple relative frequency. Now we want to combine these models using some weights. How are we going to combine them? Well, the question is, what's our goal? What's our optimality criterion? And I'd like to suggest that our goal should be the likelihood of new data. We will argue theoretically why that makes sense when we talk about information theory. But now I just want to give you that our goal is how to combine them, how to choose the lambdas when the goal is to maximize likelihood of new data. By new data, I mean data that was not part of what was used to train these models. So I can write this as a maximization problem. The lambda array, lambda vector, normalized lambda vector, that should be the winner, is the one that maximizes over all possible lambda arrays, all those that satisfy these constraints, the likelihood of new data according to my P linear interpolation model when viewed as a function of the parameters. Maybe I shouldn't write the parameters here because that's where I write my argument. I can write it here. I can rewrite it as the argmax over all these possible lambdas. Now I'm going to assume that my data was generated not independently because it was generated one word at a time, but I'm just going to use the chain rule on this from left to right. So I'm actually not assuming anything, I'm just using the chain rule. It's a product of the probability of word I given history I according to the linear interpolation model with parameter lambda. I goes from 1 to big N was the size of our original corpus. This is a different corpus. I'll call it big M. Remember, this is new data. It's a new corpus. W1 through Wm. I'm going to do one more slight transformation. I'm going to write this as argmax over all possible lambdas of the product. I goes from 1 to m. Now I'm going to write this the way we defined it, which is over there. So I'm going to open parentheses. And this is a summation of lambda j. J goes from 0 to 3 of p component j of the word given the history, word I given history I. And this is the thing I'm trying to solve now. I'm trying to find a set of lambdas that maximizes this atrocious expression. Why am I saying it's atrocious? Because it's a product of sums, and that usually stinks. It's very hard to maximize a product of sums usually. But at least I want you to be able to write it down and to understand that's our mathematical criterion. Now we have a well-defined mathematical problem. The search is in an infinite space, because the lambdas take on continuous values. It's an infinite space of 4 dimensions, right? Lambda 1, 2, 0, 1, 2, 3. But because they are constrained to sum to 1, It's a search in a manifold that is the three-dimensional manifold embedded in a four-dimensional space. That's the classic three-dimensional probability simplex. And I have to search that space for the one point in that space, one particular vector of weights that maximizes this expression. And this expression is a product of things, and each thing is a sum. So my usual trick of taking the log will get stuck. You can take the log of this. This will convert this into a sum. That's fine. But then you have a log of a sum. And I don't quite know what to do with the log of a sum. I don't have a way of... In fact, I know that there is no analytical solution to this. When I did things like this in the example of binomial and multinomial and Gaussian, I was able to solve it completely analytically, to derive a closed form solution that was the maximum. By taking the log, getting rid of constant, and taking the derivative, equating to 0, and finding the solution. There is no way for me to write this down. There's no closed form solution for this problem. And in fact, in general, when you see maximize the product of sums, the situation is not good. You can usually not necessarily find the global maximum. You can find a local maximum. But it turns out in this case we can find a global maximum. Why? Because the trick is that you have to think of this, even though it's an atrocious expression, you have to think of it as a function. What is the variable here? What is the likelihood of variable a function of? Sorry? Lambda. Lambda is the only variable here. All four of them, granted. But that's the only thing that's a variable. So you think all the others are constants. Constants, I mean, after you provide the data, they're constant. We'll only change the lambda. So if you think about it as a likelihood, if you think of the likelihood as a function of only of the lambda, it turns out it's a convex function of the lambda. And if it's a convex function, any maximum that you find will be the global maximum, because there's only one maximum. So your goal is to find the global maximum. And there are many ways of doing that. For example, you can use gradient descent. You can calculate the gradient at any particular point, take a step in the direction, and you'll get there. You can use other methods too. I'm going to show you one particular iterative method that we're going to use. But the important thing to know is that when the problem is easy, there are many solutions. And the problem here is easy. So here's the algorithm. Let me just write. Looks bad, but actually easy because it's convex. Algorithm for finding the solution. In fact, I should say that this is the argmax thing is a maximum likelihood problem, right? We're trying to find the maximum likelihood. We're trying to maximize the likelihood of some data by wiggling the parameter all possible ways. So that's solving a maximum likelihood problem. It's different than the maximum likelihood problem that was used to define these. These were defined by a maximum likelihood formulation and using the original training corpus. Then these are frozen, and now we're selecting a new set of lambdas based on new data. But it's the same formalism, so I will call this the maximum likelihood lambdas. In fact, I don't need to have a star here. I can just say the maximum likelihood solution is defined this way. So algorithm for finding the maximum likelihood lambda. First step is initialize the lambdas, which are lambda 0 through lambda k, to some value. The only requirement is that none of the lambdas should be 0. Of course, they have to sum to 1, and they have to be positive, but none of them should be 0. And the beauty is that you can start with any values of the lambdas. Remember, in a search in a convex space, it doesn't matter where you start. Anywhere you start will take you to the same place. Step number 2 is calculate something we will call weights, for lack of a better word for now. A weight for each Wi and model J. Every combination of word I and model J, I'm going to calculate the weight as follows. Zij is going to be, in the denominator, oopsie, I'm going to write the sum over lambda j pj of word I given history I. This is my summation over j, goes from 0 to k. And in the numerator, I'm going to put just one of these components. So it'll be, so this is not j, this is j prime here. Right? This is a dummy variable just for the summation. And this j is going to show up here, lambda j times pj of wi given history I. So what did I do? I took this set of weights defines a tentative model. Any set of weights define a model. So this initial set of weights defines an initial model. I'm writing down the model here and the probability it assigns to a particular word given the particular history. And then I look to see what fraction of it came from the jth component. And I call that the weight of pj when applied to wi. Maybe I'll write it a little bit better here. A weight for each pj as it is used for each wi hi combination. So there's the j here, there's the I here. So I collect these numbers. How many such numbers are there? Well, how many j's are there? 3, 4, or k in the general case. K, k plus 1, whatever you want to call it. As many as there are components to interpolate. How many i's are there? M. As many as there are words in our held out data. My third step is to...
I still have a question in the term Vij. The j in the numerator, does it also figure in the denominator? Does it come in the sum?
no, because this is j prime.
You're summing over all possible j primes.
Yes.
J prime, the set of j primes include j as well?
Yes, of course. Absolutely. So this is,
You're summing over the whole.
this itself is P linear interpolation with the particular lambda of Wi given Hi. This is the current estimate of my current interpolated model of the word I given history I. And my next step is to re-estimate the lambdas as follows. Re-estimate my new lambda j new is going to be the sum of the zij's, sum over I, divided by I think just divided by m. So what does this give me? Remember that we interpret Zij's as the weight of model J in estimating I. What fraction of the estimation for I came from model J? So this summation is like 1 over m. Well, I'm going to write it again, it'll look the same. This is basically the average weight. Average weight of P sub j. Okay? So I'm going to assign each lambda to be the average weight. And this will automatically be normalized. If I do this, all the new lambda j's will sum to 1. You can see that from here. The rest of what I'm going to do is iterate between these two. Keep iterating. Once I assign the new, I plug them into here and create new weights. And from the new weights, I'm going to re-estimate again to get new lambdas. I'm going to keep doing that until the lambdas don't change anymore, or they change by infinitesimal amounts. In other words, this process is guaranteed to converge. Converge in the sense that the lambdas will converge to a fixed point. They will not change anymore. Of course, with any finite implementation, they might change by a fraction of the representation of the floating point. But it's going to be smaller and smaller change until they don't change. And when they don't change anymore, we know we reached our maximum point. There are no tricks, no caveats. It works. In fact, it works very fast. It'll probably take 10 iterations, and it's done.
Do you give us some sort of a geometric intuition, interpretation of what exactly this algorithm is?
Well, there are many different geometric interpretations. Here's one of them. This is the likelihood map as a function of the weights, but the weights are drawn on a single dimension, even though in reality they are in multiple dimensions. Okay? They're drawn in a single dimension, so you can only move the weights this way, and every particular value of the weights will put you in a different place in the likelihood function. I'm sorry, likelihood function would look the opposite, right? Because it's concave rather than convex. It look like this. And you're looking for the maximum. You start at some random place, let's say here. Gradient descent will lead you by small steps, and you'll get here. This algorithm leads you by sometimes big steps. It might do this, and then this, and then this, and then this. Any questions about the algorithm? You will need to implement it in your homework. But it's really simple. Really, really simple. I mean, look, this is basically the only formula, and then this. And you will play with it, and you will see that, by golly, it works. Always converges to the same place. It doesn't converge if one of the lambdas starts with 0. I mean, it will converge, but it will not converge to the global maximum. The reason is, if one of the lambdas is 0, one of the lambda j's is 0, then this will always be 0. then the Zij for that j will always be 0, then this will always be 0, then it will stay 0. So 0 stays 0. Doesn't get involved. It's as if you're combining the other components without it. But as long as it's non-zero, it will find its optimal place. I want to add one piece of notation. I will show you several such algorithms that are iterative. You start with some weights and then you modify them. So I often use a superscript to indicate the iteration number. So instead of talking about a new j, I will call this initialize lambda superscript 0. And each one of these will be superscript 0 in brackets. And then these two steps can be written in terms of a general index, general iteration index. Since I, j, and k are taken, I'll use L. This is L here. This is L here. And then instead of saying new here, I will say L plus 1. The Zij's are L. In fact, I could combine these two expressions into one expression, right? Since this is a Zij, I could very easily, if I only had a eraser, I could write, this is Zij, so I can write a summation here. I goes from 1 to m, 1 over m. And now I can write Zij L plus 1. I'm sorry, not Zij, lambda j. Lambda j L plus 1 equals this. So this is the entire algorithm except the initialization. So the algorithm can be rewritten in shortened notation as lambda bar 0, init lambda bar 0, and in parentheses lambda j 0 should not be equal to 0. And then iterate lambda j of L plus 1 equals, I'm going to write it in slightly different notation just to put an idea into your head. The expected value of Zj, Z something j, conditioned on lambda L. Why did I call it the expected value? And why did I condition it to lambda L? Because all of this calculation is done in terms of the previous lambdas of iteration L. So I have to condition on that. And I call it expected value because what I'm doing here is I'm looking at the average. Did I erase it already? No. The average of Zij's. Right? I sum them and divide by m. So I looked at their average value. The reason I'm writing it in this format is because it's going to be a useful format when we generalize this to the EEM algorithm. This algorithm is actually a very special degenerate case of the EEM algorithm. So sometimes it goes by the name degenerate EEM algorithm. Some people call it, just use EEM algorithm here, but it's somewhat misleading because the EEM algorithm is often used in cases where there are lots of local maxima and you can't find the global maximum. In this case, you can find a global maximum and you don't even need EM for it. You can find it many other ways.
So, how do you find this objective function is convex or concave?
How do I know if it's convex or concave? So the rule for convexity of functions is the second derivative has to be, so if it's a function of a single variable, the second derivative has to be positive for convex and negative for concave, one or the other. More importantly, for a multivariate function, it's harder to prove. One condition is that the second derivative matrix has to be positive semi-definite, which is a generalization of being positive to matrices. But I'm not sure that that's enough, that it's sufficient. It's necessary, but it may not be sufficient. I'm not sure. Does anybody remember? Go to Wikipedia and look for conditions for convexity. In general, it's not.
I always find it very, nudging you to take the derivative of such a complex
Right.
formula.
So there may be other methods of proving it. I don't know how to prove it. I just know that it is convex.
I think you may try to prove the reference. So you take log over the linear function. It's probably convex because log is a convex function.
But log itself makes it okay. Because if the original function is convex, like the exponential, you take the logarithm, like the linear.
Right, but the original function is linear here, so you probably.
But it's a product of the linear function. Right? So outside of it, it's a product.
I do know that there are likelihood functions that look like a product of sums that are not convex. In which case, we will see it when we talk about EM. There are lots.
Is that the objective function for the EM algorithm is not convex. So generally there can be lots of local maxima, but for the degenerate case, it can be proved to be concave. And actually, the homework there's a question to ask you to prove
Great.
the case for the two-dimensional.
Good. I should do the homework then. I remember it now. I remember it now. Yeah. It's by definition, actually. When the likelihood function is convex, we call it degenerate EM. Because it is EM, it's a bona fide EM, but it converges to the global maximum. When the likelihood function is not convex, we just call it EM, and it does not necessarily converge to the local maximum. Usually it will not. I want to point out one more thing that might help clarify the homework. Running this algorithm does not require you to re-invoke the component models all the time. What you can do instead is, before you start, lay out your held out data, your new data set, W1, W2 through WM. Lay out here your model, P0, P1, P2, all the way to Pk. Calculate the probability of each one of these words conditioned on its history for each one of these models. Or do it row by row. Take one of these rows and annotate the data with its probability stream. So I call this a probability stream. This is a stream of numbers. Each one of them is the probability that this model assigns to this word conditioned on its history. So this is a probability stream. And in fact, you have 0, 1, 2, 3, all the way to k plus 1 probability streams, right? Now you don't need the P model components anymore. You can just work with the probability streams, because all you will be asked about is the probability that comes from probability stream number J prime for word I. So you just look them up. In fact, for your homework, we're not even giving you the model, the component models P1 through Pj. We're just giving you the streams. And we can ask you, what do you think these models are? But all you need for the algorithm is these streams. And in fact, those of you who are more algebraically inclined can think of this maximization problem as find the optimal linear combination of these streams so that when you combine them linearly with one set of weights, the product is maximized. So think about it as vectors. M-dimensional vectors, there are k of them, and find the optimal weights of the vectors such that when you combine them with these weights, the product of the m sums is maximized. Questions? We're on time. Thank you.